Hello and welcome to the PYB 350 Overview video series. Today we're going to talk about one-way ANOVAs in a nutshell. So in our last video we looked at experiments with just two groups, but there are many situations where we need more than two groups to give us the full information about a relationship between a particular IV and DV. We may have more than two groups of interest, such as different treatment options or different grade levels, or we may want to refine a design by adding more levels rather than just simply drug, no drug. We may want to look at low, medium and high doses of a drug versus a control group. So we could just run a series of independent t-tests, but what would happen to our type 1 error rates? Every time we ran a test, we've got a 5% chance of making an error. So if we end up running multiple comparisons, we are increasing our type 1 error rate, and this isn't so great. So ANOVA gives us an omnibus test that tells us if there's an overall effect of our IV without inflating our error rate, and then if there is, we can go in and examine where those differences lie. So the objective of an ANOVA is basically exactly the same as a t-test. So the basic objective of our t-test was to determine whether the difference between two means was large enough to convince us that it wasn't just simply due to random chance or individual differences. Yeah, we wanted to know that the difference between our means, or the effect of our IV, was so great that it wasn't likely just due to random error or individual differences. So in an ANOVA, we don't now longer have just two means because there's more than two groups. So what we do in an ANOVA is we compare the variance between the groups, which represents the variance of the differences between the means in each condition, and we compare that with the variance within groups, which represents our sampling error, or the difference in individual scores within each condition. That's essentially the foundation of an ANOVA, which is represented by our F ratio. It's just simply our between group variance divided by our within group variance. So let's have a look at some data that represents a little experiment of target identification accuracy as a function of sleep deprivation. So we have four conditions in this data set. We have participants who've been exposed to 4 hours of sleep deprivation, 12 hours of sleep deprivation, 20 hours of sleep deprivation, and 28 hours of sleep deprivation. Quite a lot. My identification accuracy wouldn't be so great after 28 hours of sleep deprivation, I'm sure. So, if we have a look here, we have a whole lot of individual scores. Yeah. From these, we can calculate the grand mean of our overall experiment. Okay, so if we add up all of these scores and divide it by n, that will represent the grand mean of our whole experiment, regardless of what group you're in. And so our total variance in this experiment is simply made of how far each one of these individual scores is away from this grand mean. Now, what we want to do is break up that total variance to understand where that variance comes from. So some of that variance is due to being in different conditions, whether you've had 4, 12, 20 or 28 hours of sleep deprivation. This is what we refer to as SS between. And this variance comes from calculating the mean for each condition, yes, and how far those means are away from grand mean. That is the variance that's due to the effect of the IV, or the effect of being in these different sleep condition groups. The other source of variance we have is our individual difference variance. And if we think about that, within each condition, yeah, the fact that everybody didn't score the same as just the overall mean of that condition is due to random error and individual differences. And so we refer to this as SS within. Yeah, so it's within each group. SS within is simply how far each individual score is away from the mean of that group. So we can look at any score and partition out the variance. Okay, this little person here didn't score, or the distance, or the reason that they didn't score exactly the same as the grand mean is in part due to individual differences and in part due to the condition that they were in. Yeah? So our SS total is made up of what's due to our effect and random error. So this person's score is not the same as the grand mean because some of the variance is due to the group that they are in, and some of the variance is due to the fact of individual differences around their group mean regardless. So we can express this through what's called the general linear model. And as we move on into complicated designs, we'll be using the general linear model to underpin our understanding of statistics. And it's the analysis tool that we'll be using in SPSS for our more complicated designs. And all the general linear model is expressing exactly what we were talking about there in the form of a linear equation. So each score is a factor of the grand mean of the whole experiment plus the effect of the group they were in plus any individual difference or sampling error or random error. Yeah? So all that's saying is an individual score is a factor of the grand mean of the experiment plus the effect plus error. We can look at this in a different way if this helps you to understand how we're partitioning out that variance in ANOVA. These are all different ways of saying exactly the same thing. We've got a total amount of variance in our experiment and we can divide that up into the between groups or effect variance and our within groups or error variance. Similarly, this is saying the same thing. Our total amount of variance is made up of the variance that's due to the effect and the variance that's due to individual differences. And this is how we express that in mathematical notation using the general linear model. Individual score is a factor of the total mean or the grand mean of the experiment, the variance that's due to being in a particular condition, how far each condition mean is away from the grand mean, and individual differences, how far each individual score is away from the mean of that condition. Okay, as we know in an ANOVA, to get from our sums of squares to our mean squares that we actually use in our F formula, we need to divide it by the degrees of freedom that are associated with that particular variance measure. So the total degrees of freedom in our experiment is the number of observations minus 1. Yep, that is the number of parameters estimated in our degrees of freedom total is simply the grand mean, so n minus 1. Our degrees of freedom between, if you remember what the formula is, we're looking at each group mean away from the grand mean. So our degrees of freedom between are a factor of the number of groups minus 1. Because the number of parameters being estimated is still only the grand mean, but now the number of observations is just each group mean. Okay. Our degrees of freedom within is based on each individual score away from the group mean, because we are estimating the mean for each group. So our degrees of freedom within are the number of people in each condition minus the number of conditions, or the degrees of freedom of group 1 plus the degrees of freedom of group 2 plus the degrees of freedom in group 3, and so on. Yeah? Just like our variance, our degrees of freedom total will add up to degrees of freedom between plus degrees of freedom within. Okay, so as we move then to our F ratio, we simply express this as MS between over MS within. That's the foundation of our F ratio. The variance that's due to the effect over the variance that's due to error. To calculate that, we base that on our sums of squares between divided by our degrees of freedom between, and our sums of squares within divided by our degrees of freedom within. And if we want the mathematical notation of that, there it is there. Yeah, how far each mean is away from the total of mean, and how far each score is away from its own group mean. So let's have a look at our ANOVA summary table then. So it will tell us the source of our variance. So we know we have our between groups variance and our within groups variance. So the ANOVA source table actually takes us through this whole process that we need to get to our F ratio. So our first step is sums of squares between, sums of squares within. Also get used to these notations as well, where we note with an A and subjects within groups. So this is just referring to the particular IV, and this is subjects within those particular groups of those IV. Because as we move on to having multiple IVs, it won't be just SS between, it'll be between relating to IV1, IV2, etc. So we have our sums of squares, our associated degrees of freedom. Remember, degrees of freedom between is the number of groups minus 1. Degrees of freedom within is the number of people minus the number of participants, I should say, or scores, minus the number of groups. That gives us our associated mean squares measures. Our F ratio then is our MS between over our MS within. Yeah? If we move on to our effect size, our eta squared is how much of that total variance is it attributable to the effect of our IV. So if you think about the logic of what we're doing, if the null hypothesis is true and our IV has had no effects, then our F statistic is simply the ratio of two different ways of estimating the population variance, and therefore it will be close to 1. Yeah? So MS within is an estimate of our population variance, the amount of individual difference there is on our DV in the population. This is an estimate of the population variance, whether the HO or the null hypothesis is true or not. However, MS between is another kind of estimate of the population variance based on the variation between our sample means. So if the null hypothesis is true and there's no difference between our groups, it's just another measure of sampling error. Yeah? However, if there is an effect of our IV, it will be much larger than our sampling error. So if you think about it, when the HO is true and our null hypothesis is true, our F ratio is just random error due to individual differences over random error due to individual differences. So it will be close to 1. Yeah? However, when the null hypothesis is false and our IV has actually had an effect, our MS between will be much larger than just a measure of sampling error. And that, in fact, is what we're testing. Is the difference between the scores in each of our conditions big enough to assume that it hasn't simply occurred due to random sampling error? Okay, so our F will be greater than 1 when our null hypothesis is false and our IV has actually had an effect. As we know, we always have some assumptions underlying our statistical procedures. In the case of ANOVA, it's independence of scores, and this is achieved either through random allocation or the fact that we're using categorical variables. That the distribution of scores in each of our groups approaches normality, and that we have what's called homogeneity of variance. That is, that the variance of scores around each group mean is similar in all our groups. And this is important because our error term is actually what's called a pooled error term. It's based on the error in each one of those groups, and we pool it together as an estimate of our population variance. Okay, so homogeneity of variance is a key assumption of our ANOVA. So let's have a little look at an example now. So, evidence suggests that sleep deprivation affects temporal memory, and this experiment explored the effects of 36 hours of sleep deprivation on a neuropsychological test of temporal memory. The test was short, novel, and interesting, and caffeine was used in some conditions to reduce sleepiness. So 28 young adults were randomly allocated into 4 groups. They were either in a control condition where they had no sleep deprivation and received caffeine, in a control condition with no sleep deprivation and they received a placebo which did not contain caffeine, or they were in a sleep-deprived condition and received caffeine, or in a sleep-deprived condition and received a placebo. And as I said, control slept normally. Caffeine was either 350 milligrams of caffeine or a placebo, and the sleep-deprived group were exposed to 36 hours of sleep deprivation. Okay, the task comprised colour photos of unknown faces and a test of recency discrimination for a previously shown face was presented, and that formed the DV. Okay, so here is the data for our experiment. Here is our 4 different conditions. Yep, control caffeine, control placebo, sleep deprivation caffeine, sleep deprivation with a placebo. There's all our individual scores for the participants in each one of those conditions. Here's the mean for each one of those conditions. If we add up all of those scores, here is our grand mean, or the total mean of our experiment. We had 7 people in each cell, 28 people in the whole experiment, and there were 4 conditions. Okay. Let's look at our output that we'd get if we ran that data through SPSS one-way ANOVA. Okay, so the first thing we'd get is our descriptives. So very clearly the number of people in each cell, the mean of each cell, standard deviation, standard error, and the confidence intervals around those group means. Then we would get our Levine's test of homogeneity of variance. So it gives you several different estimates of that, depending on whether it's based on the mean, the median, or the trimmed mean. As an ANOVA is about comparing means, we're interested in the based on the mean line. And what we want is a non-significant Levine's test, because we want the variance in each of those groups to be similar. So we want our Levine's test to be non-significant. So in this case, we have a non-significant Levine's test, so our homogeneity assumption has not been breached. Then we get our ANOVA summary table, and here we have it. Our between groups sums of squares, our within group sums of squares, which add up to our total sums of squares. Associated degrees of freedom, we have 4 groups, so our degrees of freedom between is 3, degrees of freedom within is 24, our 28 minus the number of groups, 4, and they will add up to our total degrees of freedom, which is the total number of participants minus 1, 28 minus 1. We divide our sums of squares by our degrees of freedom, we'll get our mean square between and our mean square within. Our F ratio then is our mean square within divided by our mean square within, to give us an F ratio of 25, which is significant, suggesting that our IV has had an effect. Yes, we just don't know where. Now, I'll just give you quickly a little look at the output that we would get if we carried this out via the general linear model analysis tool in SPSS rather than one way, because this is the tool that we are going to be using when we move on to our factorial ANOVA designs. So we get the same information regarding our descriptives, the means and standard deviation for each of our conditions, but our ANOVA summary table looks a little bit different because it is using the general linear model. But obviously, it's going to be telling us the same thing. In this case, our IV is represented by group, which one of those groups the participants were in. So that is just our between group variance. Our error variance is our within group variance, and our corrected total down here at the bottom is our total variance. So you can see the figures in there are exactly the same. You just need to be able to recognize which lines you're interested in. And of course, our F ratio and significance levels are the same. I've also, in this output, asked SPSS to calculate our eta squared, which is 0.76, which tells us that 76% of the variance in the scores in those groups is attributable to which group the participants was in. So quite a strong effect size. So the measure of effect size that is most often reported for ANOVA is eta squared. And as I said, that is simply SS effect over SS total. So in our example, it was 0.760, which tells us that 76 of the variability in recency discrimination was associated with the differences in that sleep caffeine group status. Do note that eta squared is a descriptive statistic and it does slightly overestimate the effect size. Next video where we look at how you follow up an omnibus ANOVA test to look at where those differences actually lie. We'll talk a little bit more about other kinds of effect size that you can use to look at the effect size of differences between actual pairwise comparisons. Terrific. So that's it for one-way ANOVA in a nutshell.